right? So the initial motivation of discussing or inventing IPv6 was that the 32-bit address space of IPv4 has been completely allocated. So we do not have the pool of IPv4 addresses available. So we need to come up with a greater address space, right? And the additional motivation was to, come up with a header format that speeds up this forwarding process or processing, right? And that's why we will see in a minute that the header of IPv4, IPv6 is very simple, and because of this, the overhead is only 0.06%, right? So this overhead is only 0.06% now, and the header has been changed to facilitate quality of services, and for that we'll see that we have a priority field. For that we have here the priority field, and we also have for that matter we also have the flow label, right? And also the IPv6 datagram format has a fixed header. Its header is not variable, and most importantly, we have discussed it earlier that it does not allow fragmentation and reassembly, which really makes the job of end machines and routers simple, because then now these machines and routers do not need to do the fragmentation and reassembly. Okay, so if we look at the header of IP version 6, so here we have the version field, which is IP version 6 at the moment. Here we have the priority field, and this priority field is in fact type of service field, similar to the type of service field in IP version 4, right? It's 6 bits are used to identify the different classes of application or path of behavior in real-time applications, and then we have this flow label. Initially, as it's also written here, it's not well defined, and initially these bits were reserved, right? Initially, these bits were reserved. But these bits can be used to identify that a datagram belongs to the same flow. Then we have this payload length, which tells us the size of the data in the data field. Right? So this gives us what? The size of the data. Okay, and then we have the next header, means what is the next header here? I mean, either we are having this TCP segment here or UDP segment. If it's a TCP segment, the next header would be of TCP header, right? And then we have this hop limit. This hop limit is basically as a functionality similar to TTL. It's the other name of time to live, and we know the time to live field is there to make sure that a packet is not endlessly circulating inside a network, right? So, and then we have 28-bit source address. So here the address bit is very large, right, as compared to the 32 bits of 32-bit address of IP version 4. And what they're anticipating is that this address space is so huge that even the sand particles can be assigned IP addresses, right? So this IP address is basically this 128-bit source and 128-bit destination IP address is written as 816-bit integers, separated by, right? And each of these 16-bit integers are represented by 4 hexadecimal digits. So we know that The IP version 4 address is a dotted decimal number such as 172.16.17.4, right? But when we talk about this IP version 6 address, so this IP version 6 address is basically 8 16-bit integers where each of these 16-bit integers are represented by 4 hexadecimal digits such as, let's let's have a look at the example of IP version 6 address. So this can be possible IP version 6 address. So 4EDC. So these 4 hexadecimal digits separated by a column. Then we have again 4 hex digits separated by a column. Separated by a column. Nine, 8, column. Okay, so you can clearly see that here we have 8, 1, 2, 3, 4, 5, 6, 7, 8. Here we have 8. Here we have 8, 16-bit integer, and each of these 16-bit integer is being represented with 1, 2, 3, and 4 hexadecimal digits. Okay, so this is how the IP version 6 address is represented. Okay, so we can also note here is that there is no options field here in this IP version 6. So we have no options field. So that's why its header length is fixed. But the option field is not completely eliminated. We can still have this option field, but outside the header, and this is indicated by the next header. We can have this option field if we want, right? But this can be indicated. This can be indicated by this next header field. But most importantly, this is not the part of the header of the IP version 6 directly, and that's why its overhead is less. Why? Because the error checking is already being done at the transport layer. So the argument is there is no need to do it again at the network layer. Okay. So the other changes, as we have discussed, that there is no checksum here, and the option field is implemented as next header. And most importantly, since it does not allow, since the IP version 6 does not allow fragmentation and reassembly. Right, so that's why we need to come up with the new version of ICMP version, and that is ICMP version 6, and where we have a new type of message that is packet to big. So if somebody is sending a segment of greater than, say, 576 size, 576 bytes, so this means the router will generate a message indicating that the segment is the router will send a message indicating that the packet is too big. So we have a new version of ICMP, that is ICMP version 6 for IP version 6, where we have included an additional message with indicating the packet size, since the fragmentation and reassembly is not allowed in IP version 6. So since the IP version 6 has been around quite long as a part of the operating system, but the problem is that we have not been able to have a transition from IP version 4 to IP version 6. It is the fact that IP version 6 routers are backward compatible and can cater IP version 6 traffic, but we cannot upgrade IP version 6 enabled router at once. So there can be no flag days that's where we say, okay, fine, that we have changed all the IP version 4 enabled router devices to IP version 6. So this means we have to come up with a transition strategy where we have to make transition from IP version 4 to IP version 6. And there are different approaches for that. One is to do the tunneling, right? We'll see in a minute. And the second is to have dual stack. Right, so let's try to understand that how we can make a transition using either tunneling or the dual stack. So in dual stack, what happens is that this router B is dual stack, can operate on IP version 4 as well as IP version 6. So what it will do is that if a packet comes from IP version 6 enabled router, say A, and the next router is C. So what it does is that it generates IP version 4 packet. So in this case, I'm talking about the dual stack arrangement implementation. So this means the router B will not be including many of the header options of IP version 6. The problem with dual stack application is that implementation is that so we might lose many of the header details and implementation, like quality of services, type of service, right, or priority or row labels in its implementation, right? So the other possibility that is represented in this slide is tunneling. So what it does is in tunneling, this is the physical view, by the way. So what the router B does is that it encapsulates IPv6 into IPv4, right? So this is IP version 4 packet. This is IP version 6. So IP version 6 is encapsulated inside IP version 4, right? So all the routers, which are many representing the core network, will deal with this IP version 4 IP version 4 data packet, right? So when it reaches the IP version 6 enabled router, it will extract IP version 6 data packet and will forward the data packet, which is IP version 6, to the next IP version 6 enabled router. So we can start doing transition at ends where we will keep on updating, changing the IP version 4 routers into IP version 6 routers, and up to that we can use this tunneling. So you can see that there is a tunnel from A to E, where what we are doing is basically where we are encapsulating IP version 6 packets into IP version 4 packets, right? And what is happening in the dual stack? In dual stack, this B will in fact represent the data that was being carried by IP version 6 in IP version 4 by ignoring many of the header implementation of IP version 6. So this is the possible strategy of transition from IP version 4 to IP version 6, which is being, by the way, followed at the moment.